let us now inquire into what happens when f of t is differentiated in time domain, what is its effect in the transform domain. So, we will say differentiation in time. In time domain, what is its effect in the transform domain? If f of t and f of j omega form a transform pair, then this particular property tells us df by dt, which may like to call f prime t, has its Fourier transform, which is obtained from the original Fourier transform by multiplying by j omega. That is all. So, differentiation time domain corresponds to multiplication in transform domain by j omega, and this is one of the very useful properties of a transform of a particular time function, because the calculus that is involved in the differentiation is replaced by an algebraic multiplication j omega, and this is a trend which you will notice as we go along, not only in Fourier transform, but Laplace transform also, that operations involving calculus, integration and differentiation are converted into multiplication or division by j omega, and this makes for a great convenience as far as working is concerned. We will talk more about this later, but let us see why this is so. F of t can be obtained from f of j omega to the inverse transformation, that is f of t can be written as 1 over 2 pi from minus infinity to plus infinity of f of j omega e to the power of j omega t d omega. Now, let us differentiate this signal. So, df by dt the derivative of this with respect to time is df by dt, and assuming that we can differentiate under the integral sign here, if you carry that out here, this will become 1 over 2 pi from minus infinity to plus infinity f of j omega e to the power of j omega t d omega, because this is the only function of time inside the integral sign. So, what we have here is a quantity f j omega multiplied by e to the power of j omega t d omega. So, obviously, whatever we are having here is obtained as 1 over 2 pi times minus infinity to plus infinity plus some quantity function of omega into e to the power of j omega t d omega. This is the defining relationship of an inverse Fourier transform. Therefore, df by dt must be the inverse Fourier transform of f of j omega j omega. So, that is what we have here. If we have j omega f of j omega, its inverse Fourier transform is df by dt, or in other words df by dt f j omega f j omega is the transform of df by dt. So, this is a very useful result, and to illustrate this, let us work out an example once again. Let us take a simple signal f t is e to the power of minus a t u t. Let us work this the Fourier transform of f dash t in two ways. One, by straightforward method, by differentiating this and then trying to find out its Fourier transform, or alternately finding out the Fourier transform of this and then find out the Fourier transform of the differentiated signal. So, what we would like to find out is Fourier transform of f prime t is what? This is what we want to know. So, method 1, Fourier transform of f of t. This is a function which we have been talking about all the time, is 1 over j omega plus a. So, the Fourier transform of the derivative function f prime t is j omega over j omega plus a. That is all there is to it. It is quite simple and straightforward. Now, we would like to check on this result by actually carrying out the differentiation in time domain and finding out its Fourier transform. So, let us see what it is. This is the function f of t. This is 1, this is e to the power of minus 8. If you plot the f prime of t, its derivative, e to the power of minus a t, its derivative will be minus a e to the power of minus a t. So, you have minus a e to the power of minus a t, that is the second. Now, that is not all. Why? The Fourier transform considers the time function from extending from minus infinity to plus infinity. Therefore, you must take the derivative at every point. Now, you observe this f of t was 0 all along, and suddenly it jumps to a value 1. Therefore, at this point it jumps from 0 to 1. Therefore, there is the derivative must be infinitely large, and that quantity when integrated must give rise to 1. Therefore, obviously, what you are having here is a delta function of magnitude 1. So, f prime t really is not simply given by this alone, but also you must have a delta function. So, in other words, f prime t is equal to delta t plus this quantity, which is minus a e to the power of minus a t u t, because this function starts only from t equals 0 onwards. So, f of j omega for this, the Fourier transform of f prime t would be the Fourier transform of this plus the Fourier transform of this. The Fourier transform of delta t is obviously 1, and e to the power of minus a t u t as 1 over j omega plus a, except that we have one more a here and a negative sign. So, minus a over j omega plus a, and this is indeed j omega over j omega plus a result which is in accord with this. So, the important fact that this example brings up is, for one thing, when you are taking the differentiation, you must also consider the derivatives associated with jumps as shown here. And secondly, to find out the Fourier transform of a differentiated signal, you do not have to carry out the differentiation time domain. If you know the Fourier transform of this signal, all you have to do is multiply by j omega. So, this makes, as I pointed out, for a great convenience in manipulation of differentiated signals. Now, I would just introduce a topic, but we will not carry this out. What one might argue is, if differentiation is equivalent to multiplication by j omega in time domain, would it mean that integration will be equivalent to division by j omega? But after all, this signal is obtained by integrating this signal. Therefore, if you have some Fourier transform for that, the Fourier transform of the original signal must be obtained by dividing this by j omega. This is true up to a point, but it is not quite true. In other words, what we would like to point out and postpone the discussion to a later stage, integration, if f of t has a Fourier transform f j omega, then integration then must also fix the limits from minus infinity to t of f of t dt. What is its Fourier transform? Is this f j omega by j omega? This is the question which we would like to ask. The answer is not always so. So, we must be careful in trying to integrate a signal and finding out its Fourier transform. We will discuss this at a later point of time after we find out the Fourier transform of a step function. So, we will postpone the discussion of this. So, what I would like to caution you at this stage is, you should not jump to the conclusion that because differentiation involves multiplication by j omega, integration means division by j omega in the transform domain. That is not so. We have so far said how certain operations in the time domain, how they are reflected in the transform domain. For example, we saw how the function of time is shifted in time, what is its effect in the transform domain. When it is differentiated in time, what is the effect in transform domain. These are properties we have studied. Let us now continue this trend. We will take up now the case where it is reversed in time. So, if f of t and f of j omega form a transform pair, we want to know what is the corresponding f of j omega for f of minus t. If the sequence of events take place in the reversed direction, what is the corresponding f of j omega? The answer simply is f of minus j omega. It is straightforward to show this, because after all you have now minus infinity to plus infinity of f of minus t e to the power of minus j omega t dt. You can replace, let minus t be x, then I can write this as f of x e to the power of j omega x minus dx. For dt I will put minus dx, and when t equals minus infinity, x will be plus infinity, and when t equals plus infinity, x is equal to minus infinity. And this can further be written as this minus sign, and these integral limits can be taken care of by putting this plus sign and reversing the integral limits. Therefore, I can write this minus infinity to plus infinity of f of x e to the power of minus j minus omega x dx. So, instead of plus omega x, I put minus omega x, therefore, I introduce a minus sign here. This of course can be written as minus infinity to plus infinity. After all, x is a dummy index. This is f of t e to the power of minus j minus omega t dt. So, the difference between the defining relationship for the Fourier transform of f of t and this is, instead of plus omega, you have got minus omega. Therefore, this is f of minus j. Right. And what is the further significance of f of j omega? For real signals f of t, that means whenever you substitute a real value of time, the f of t also turns out to be real, then it turns out that f of minus j omega equals f of j omega conjugate. That means the angle will be angle will be reversed, but the magnitude will remain the same. You can write this also as f star j omega. That is, in other words, the conjugate of f of j omega. Again, according to our practice, let us work out an example. This time function e to the power of minus a t u t, we know has the Fourier transform 1 over j omega plus a. Now, I would like to inquire about the Fourier transform of a time function which is given by e to the power of minus a t for positive t and e to the power of plus a t for negative t. That means, this portion is e to the power of minus a t. It is a reflection on the negative side, this will be e to the power of a t, because for negative t the exponent will become negative and again it decays. So, this f of t that we have now can be described as f of t is e to the power of minus a magnitude t. So, the composite curve can be described analytically in this fashion. Now, what is the Fourier transform of this? It is quite straightforward, because we know the Fourier transform of this section. the Fourier transform of this section is 1 over j omega plus a, we know that. And what is this time function, how is it related to this? If this is f of t, this is f of minus t. The whole sequence of events that take place in the positive time axis will now be taking place in the negative time axis in the same order. Therefore, the Fourier transform of this, if it is f of j omega, the Fourier transform of this is f of minus j omega. And after all, what we have here is this nu f of t is the summation of these two curves. Therefore, we can say its Fourier transform is, the Fourier transform of this is 1 over j omega plus a, and the Fourier transform of this portion is 1 over minus j omega plus a. So, this particular f of t, which you have given e to the power of minus a magnitude t, will have a Fourier transform which is 1 over j omega plus a plus 1 over minus j omega plus a. And you combine these two, you get denominator a squared plus omega squared, and in the numerator you have 2a. Now, the essential motivation for our study of the various properties of the Fourier transform is to find shortcuts to find the Fourier transform in this manner. You do not have to try to integrate this in both directions and get the result. Once you know the property, you would easily deduce the Fourier transform of this in this manner. So, this is the real motivation for our study of the various properties of the Fourier transform, so that we can intelligently obtain the Fourier transforms of certain functions and also find the inverse Fourier transforms of certain functions once you know these various properties. Okay. Let us now continue with our discussion with an additional property where we are thinking of scaling in time domain. So far we have talked about translation in time domain, reversal in time domain, differentiation in time domain. Now, let us consider what happens if you scale the function in time domain. Again, we start with the basic f of t, f of j omega pair. Then I would like to know what is the Fourier transform of f of a t, where a is real and positive. Then it turns out to be this 1 over a f of j omega over a. Okay. Now, how do we establish this? Proof is again straightforward. We take the Fourier transform of f of a t, which is minus infinity to plus infinity of f of a t e to the power of minus j omega t dt. Now, by this time you must have got an idea of how to go about this. You must substitute some x for a t, so that we will try to bring this into a form which we can compare with the Fourier transform of f of t. Therefore, if you substitute x for a t, then this becomes, when t becomes minus infinity, x also becomes minus infinity. When t becomes plus infinity, x also becomes plus infinity f of x, and e to the power of minus j omega t equals x upon a, t is x upon a, and by dt is dx upon a, dx upon a. So, this is obviously 1 over a from minus infinity to plus infinity of f of x e to the power of minus j omega by x dx. And since the dummy variable x as the integration, I can as well replace it by t. This will be f of t e to the power of minus j omega by a times t dt. And this clearly is this. 1 over a times f of j. Instead of omega, you have got omega by a. Therefore, in the defining relations for f of j omega, you would have j minus j omega t. But instead of omega, you have got omega by a. So, instead of being f of j omega, it becomes f of j omega by a, and this a is sticking outside. That is what it is. So, this again has got some important aspects in relation to scaling of time functions. Let me illustrate this. Illustration of this. Suppose we had a time function which is given like this, a and stretching from over an interval d, and let me imagine that its Fourier transform would be like this. Magnitude spectrum I am plotting, and this is equal to, say, let us say some omega, I will say some omega naught, whatever it is, and then this is here. This is the Fourier spectrum for this magnitude spectrum. Now, let us see what happens if I compress the in the time scale. That means the events now come closer together. So, I have the same a, but the events occur faster. So, this is d upon 2. So, the same information, the sequence of information events are now compressed in time. They are occurring over a smaller interval of time, d upon 2. So, if this is f of t, this will be f of 2t, because at a smaller value of t you get the same original values. Now, what is its consequence on the spectrum? From what we have seen here, first of all, f of a t 1 over a, the amplitude must go down by a factor half, and then omega by a. So, it means j omega by 2 it becomes, that means it gets spread out. So, that means the amplitude is like this, it goes like this. So, this will become m upon 2, and this will become 2 omega. On the other hand, if I allow the things to take place more leisurely, so let us say this is 2d and this is a, this will be f of t upon 2. That means it takes a longer time for a particular value to reach compared with this. The t must be doubled to achieve the same value what it had in case of f of t. So, in this case a is equal to half in the original formula that we have here, a equals half now. Therefore, it means as far as the spectrum is concerned, it will be 2m. This means this will become larger, but 2 f of 2 j omega. Therefore, in the frequency spectrum things become crowded now. So, it means it will be very large compared to this, and this becomes omega upon 2, omega naught upon 2, and this will be 2m. So, what it really means is, the significance of this is that if you allow certain events to come faster, then it requires has larger frequency components. Compared with this, you have got certain frequency components, and then this spectrum is spread out. That means you have more high frequency components. So, if you have a time signal in which events occur faster, then it requires higher frequency components. On the other hand, the same sequence of events take place in a more leisurely fashion. That means they get more of lower frequency terms come into the picture, and their amplitude also go up. That is what it is. Things which occur faster involve high frequency components, and things which occur in a slow fashion as a greater concentration of low frequency components. So, in other words, the slower the rate of change, then you need to have a smaller bandwidth as far as information transmission is concerned. But on the other hand, if you like things to happen fast, if you have got faster changes, then you require a larger bandwidth because higher frequency components are more. So, this is an important property in information transmission, which we can say information sent at a faster rate needs to have has higher frequency components, and therefore, the channel must also have the corresponding bandwidth to handle such signals. If we have seen now that f of t, if it goes f of j omega, f of a t is 1 over a f of j omega by a, and we assumed a is positive, real and positive, so that we are talking about a being greater than 1 and less than 1, and we talked about this. It will be of interest for us to know what happens when a is negative. Then it can be shown that if a is negative, f of a t as per its Fourier transform 1 over a magnitude f of j omega over a. So, all it means is the magnitude of a comes into the picture rather than the actual absolute value, the actual value of a. So, this is a result which can be derived on the same basis. So, all it means is the scale factor is now depends on the magnitude of a, even if a is negative. So far we have studied several properties of the Fourier transform. You recall we talked about the linearity of Fourier transforms, then various operations in the time domain like translation in time domain, then multiplication by an exponential factor e to the power of j omega c t, then we talked about differentiation in time domain, then we talked about time scaling, and we talked about reversal in time domain, and saw what all these operations in time domain, how they are reflected in the transform domain. A study of all these properties will help us to find out the Fourier transforms of certain functions in much more in a simpler way than if we had to resort to direct integration, and also when sometimes we want to find the inverse Fourier transforms, that means f of j omega is given and we want to find the corresponding f of t. If we keep these properties at the back of our mind, sometimes we get at the solution in a more straightforward way.